So welcome to part 2 of lecture 18. In the last part, what I presented was a theorem that gives us a criterion to tell us when our basis that we picked will give us a basis that allows us to show that the matrix associated to the linear operator is upper triangular. And we're going to prove it now. Okay, so let's move over to my next page. So first of all, we're assuming that our basis has been picked so that the matrix associated to it is upper triangular. Okay, now what we said at the very beginning of the very first part of today's lecture is that the jth column records what happens after we plug the vector vj into our linear operator, right? So this means that normally we would have tvj would be written in terms of its basis, so it would look like a1j v1 all the way up to ajj vj plus aj plus 1j vj plus 1 all the way to a and j vn. But notice that in this column, right, so here's the jth column that we're looking at, right? It's telling me where vj gets sent, and here you have a whole bunch of zeros below once you get below the ajj, or below the ajj. So all of these guys, right, are 0. So we can rewrite this as simply a1j v1 up to ajj vj, and this is definitely an element in the span of the first j basis elements. So this is what we needed to prove to show that 1 implies 2. Okay, what about the converse? Okay, let's say now we take a vector that's in the span of v1 to vj. Okay, so this means that tvj, because it's a linear combination of these vectors, can be written as b1 times the first vector plus b2 times the second vector all the way to bj times the last vector. Okay, but we can now add in kind of some dummy elements, right, by multiplying by things by 0 in the correct way. So we have b1 times v1 all the way up to bj times vj, and then 0 plus 0 times vj minus plus 1 all the way up to 0 times vn. And this now tells me what the jth column of the associated matrix is going to be. These are going to be, all of these numbers or coefficients that show up here are going to tell me the jth column. And so I've started that over here on the next slide. I will have something that looks like this. So here's my jth column. And I will have b1, b2 up to bj, and then all the way down to 0, right? And this bj will actually be in spot j. Now this is going to be true for each of the columns. So in the first column, I'll have a something here, maybe it's 0, maybe it's not, but the rest of the elements are going to be 0. In the second column, I will have 2 things in the first 2 spots, but then the rest of the things will be 0. So I end up with an upper triangular matrix. So MT is upper triangular, okay, since all entries below the diagonal are 0. Okay. Now, I'm actually going to prove the equivalence of 3 and 2, these two things right here. It's actually not too hard, and maybe I want to encourage you to try to write out your own proof for the equivalence of these two things. Okay. So just to kind of set up where we're going to go into the next part, because we're going to spend a little bit more time on the next part, is we want to show that as long as you have a complex, a vector space over the set of complex numbers, there actually is a basis that you can pick so that the matrix is upper triangular. So we'll work out all the details of this in part 3.